Wilson in Electrical and Computer Engineering and Institute for Systems Research. And it is my great pleasure to introduce Piya Pal, who's an assistant professor, a fairly new assistant professor, started in January here in the ECE department. Piya received her PhD in electrical engineering from Caltech in 2013 and her BTech in electronics and electrical communication engineering from IIT Kharagpur.
That's right, Kharagpur, yeah.
India in 2007. During the course of her PhD, she developed novel techniques for non-uniform sparse sampling, which received a Best Student Paper Award at the 14th IEEE DSP Workshop and the 45th Asilomar Conference on Signal Systems and Computers in 2011. Her research interests span compressive and structure sampling, statistical signal processing with applications in radar and array processing, tensor methods, and statistical learning. Piya also received the Charles and Ellen Wiltz Prize for Best PhD Thesis in Electrical Engineering in Caltech, quite an honor. And she's also been the winner of an Everhart Lecture Series at Caltech as well in 2013. So we'll get started, and let's welcome Piya.
Thank you, Carol, for the really nice introduction. It's my honor to be here to present my research in front of a diverse audience. And I really look forward to your comments, suggestions, and questions, both during the presentation and also, towards the end. So today, my topic of the talk is going to be sampling beyond Nyquist. So it is a very broad range of topic where I'm trying to bring 2 or 3 subtopics under the same umbrella, where I'll show how structure, geometry, and statistical prior information can work hand in hand to push sampling limits much below Nyquist and even much below what is traditionally known by exploiting only one of these structures. Okay? So the sampling theorem essentially connects 2 worlds, right? So there is an analog world where your analog signals reside. Most physical signals, most naturally occurring signals will take the shape of an analog signal, right? So they're continuously varying signals, mostly continuous functions of time, though they don't need to be. And the digital world, of course, is a man-made world where we sample the signals and represent them in the most efficient way possible, okay? And of course, our life hovers around all digital media and the signals that we process every day using smartphones, laptops, everything that we use, right? Now, the sampling theorem actually sits at the intersection of these 2 worlds. You can go from analog to digital world through A to D conversion, and provided you can also reconstruct it back, which is the D to A conversion. At a very basic level, this is the connecting thread. And the Nyquist-Shannon Sampling Theorem actually is a guarantee that you can do these things without any loss of information. So you can sample as well as reconstruct without any loss of information. So this sampling theorem gives you the sampling rate at which it has to be done so that there is no loss of information in the ensuing process. Now, if you really look at this Nyquist sampling theorem, which is kind of at the core of DSP. So DSP starts with the assumption that, okay, my analog signal was sampled at the Nyquist rate to begin with, and then we do whatever processing we have to do with those samples, right? So actually, the Nyquist sampling only considers the representation of the signal in the frequency domain. That's all it cares for. It doesn't necessarily exploit any additional structure or information that you could have exploited in a signal. So all it does is look at the frequency content of the signal, and it says, okay, depending on what the highest frequency is, in case it's a band-limited signal, I'll kind of roughly sample at twice the highest frequency and get my samples. So you can also think of this sampling process to be only looking at one kind of representation. But today, signal processing has become akin with data processing actually. And your data is much more complex than what it can be only described in terms of a frequency parameter, okay? So your data, these days, the high dimensional data often has as a hidden low dimensional representation, a low dimensional structure. And depending on your source, on how the data is, what the data is, those structures can take different forms. The structure can be in the form of sparsity, okay, which means that, okay, there is a lot of redundancy in your data, or your data is composed of only a few atoms from an appropriate dictionary, if you can represent the data in that appropriate dictionary, okay? Or depending on what class of signals you're looking at, if you are looking at matrices, matrices inherently can have low rank, and that can arise because of physical phenomena, right? So low rank sparsity, they are all ways to characterize something which occupies a lower dimensional representation, but the samples that you're observing belong to a high dimensional space. Interestingly, statistical priors can also play a big role in bringing down the sampling rate, okay? So sometimes the data that you consider, it will typically have a lot of correlation, and correlation means the data is redundant in some way, okay? So provided you can make use of the correlation, then probably you can only reduce the data to a lower dimensional sample space where you can do your operations, which will bring down your computational complexity as well. So the moral of the story, or the gist of this slide, is frequency domain is not enough to represent all this saliency that is present in the data in today's modern data processing tasks. And of course, we know that we live in a world where we encounter big data every day. It comes in all shapes and sizes, arises in all these kind of applications, okay? And that basically necessitates the need to rethink sampling and rethink our way of how we can exploit structure in sampling. Now, why do you want to compress a signal? Of course, you can have efficient representation, you can have more efficient algorithms which work on lower dimensional signals. But in the end, from those measurements, your end goal is, in many cases, is to do information processing, right? You want to extract some information from those measurements. And you can think of this information as an inverse problem. Sometimes you're not really interested in recreating the entire data from your samples, okay? You're not interested. You're interested in maybe estimating some parameters. So if you know that your end goal is only to estimate certain parameters from the data, can you sample it at the sampling stage itself? Can you perform dimension reduction so that you kind of get rid of things that you do not need, okay? So that is why we have to think about sampling as a means to bring down the complexity in information processing than just to recreate the data itself, okay? So the point is, although your number of measurements is available is large, but your information content can be small in the appropriate domain of representation. So for instance, I'll give you two examples which will kind of motivate you. So one example is, when a radar flies, it kind of collects data in a data cube. It collects data in space, time, and angle, okay? And in Doppler, sorry. So Doppler means it basically looks at the velocity of the signal as well, of the target as well. And its goal is to basically, in that data cube, its goal is to find some distinct points, actually. So it has a huge number of data, but those data are actually some kind of dependent only on a very, very few parameters. Those parameters of interest are distance, direction, and velocity. So if you know a priori that that's what you're looking for, can you bring down your sampling schemes? Or can you bring down your sampling rate further than what is taken to be granted, okay? Another example is, so for instance, this is a classic example where low rank of a matrix comes into play, okay? So I think all of us have Netflix accounts, or we have watched Netflix at some point of time, right? So Netflix had this problem of doing user ratings. So it has like so many users and so many movies, and not all ratings are available for all the movies. So it wanted to predict what a user might rate, how a user might rate a movie which is not, whose rating is not available. So in that case, the entire fact that this prediction is possible by looking at only a few samples which are available hinges on the central assumption that there are only a few factors that influence an user's rating. So there are some latent factors which we do not know, which we probably want to learn, that influence a user's rating. So probably he likes a certain genre of movie, or he likes watching a certain movies coming from a certain director. So that assumption, that key assumption, makes it possible also to interpolate the data, okay? So even if you have a very, very small subsample set of your data, it is possible to recreate the missing samples just by observing that you have redundancy in your representation. So naturally, the question that I'm trying to answer today in this talk is how few can your sampling, how few samples you need, or how small your sampling rate can be, and how to acquire those samples, and from those samples, how do you extract information? Okay, because you're working on a very subsample space right now, your traditional estimation algorithms may or may not work. So you have to be clever. And typically, this stage is often the hardest stage. Typically, you will see that sampling strategies sometimes can be as simple as random sampling, provided you can reconstruct your information from those random samples. So today, in today's talk, the binding theme will be correlation, using correlation as a guiding prior. Okay, and I will give you 3 concrete problems which I will discuss. Depending on how fast I go, I'll discuss them in different details. So the correlation is basically looking. So you have data. So you are only interested in looking at the correlation of the data for whatever reason. Okay. So there are applications which consider this, which start from this correlation computation and develop the algorithm based on the correlation in data. So there are tons of such algorithms. The most common algorithm which directly relates to correlation computation is that of spectrum analysis, because spectrum is nothing but the Fourier transform of your correlation sequence of a signal. So, but not only that, it also finds application in a variety of learning tasks and data dimension reduction tasks. So principal component analysis also looks at the correlation matrix of your data to reduce the dimension. Okay, so how can we use the correlation information in our data to bring down sampling rates and to extract information from the subsampled correlation values is going to be our topic of discussion today. So the first topic that kind of exploits the correlation of your signal is that of spectrum sensing, and I will introduce a new sampling technique that I developed during my PhD called the coprime samplers, which will perform spectrum sensing at a much smaller sampling rate without using sparsity. So there are lots of papers available which say that, okay, you can do spectrum sensing at a sub-Nyquist rate because your spectrum is sparse in some way. But I'll show that your spectrum does not need to be sparse. If your spectrum satisfies certain conditions, or if your correlation sequence satisfies certain conditions, then you can do spectrum sensing at a sub-Nyquist rate just by exploiting that information without imposing any sparsity. Okay? So what I mean by that is, if you have a wide-sense stationary signal, which is a very common signal that arises in a variety of signal processing and communication tasks, what happens is a wide-sense stationary signal, you can think of it as a random process, whose correlation sequence only depends on the difference in the sampling instance of your sequence. So let's say you have a sequence x of n, and you compute correlation between 2 samples separated by some distance. It turns out that the correlation only is a function of the distance and nothing else. So at which point you measure those samples do not matter. They kind of become irrelevant. Only the differences matter. Okay? And of course, you get the correlation sequence in this fashion, and you take the Fourier transform, that is your power spectrum. So very just follows from the definition. And spectrum sensing has been there for a while, for quite a few decades, I would say. It is a classical signal processing task. And in most classical spectrum sensing applications, you will find that the samples, so these sequences are already sampled version of some analog signal, right? So it is assumed that these samples were acquired to begin with at the Nyquist rate. And what was the Nyquist rate? The Nyquist rate was basically the highest frequency present in this wideband signal. So if your power spectrum is a wideband spectrum, which is the case for cognitive radio, where you kind of span across a huge band of frequency to look for available holes in the spectrum, this sampling frequency can be pretty daunting. Okay? Now the point is, do we really need to sample at that high frequency, or can we be clever about it? Okay? So just to get you started with this idea, imagine that we did not sample at the Nyquist rate. So imagine 1 over t was a Nyquist rate, but we sampled that with 2 different samplers which operate at m times t and n times t, where m and n are 2 integers. Okay? The point is, using these sequences which are drastically undersampled, can I recreate the autocorrelation sequence at the Nyquist rate? Okay? So my signal to begin with is highly sub-Nyquist sampled, but my goal is to make my autocorrelation sequence, think of it as another signal, right? To make it dense, in the sense that the sampling should be dense. So whether or not it's possible to do that, to understand that, look, if we consider a bunch of sampling instances at which sample the sequence and got those instances, right, n1 to nk, it is really the difference of this these samples that matters, right? Ni minus nj, and nothing else matters. That's what decides at what instance the autocorrelation sequence is sampled. So if you understand that, then if you look at the traditional uniform way of sampling data, okay, what it does is it consists of a certain interval, and it kind of takes all possible integer multiples of that interval and places its samples at those points. So it's called uniform sampling. They're uniformly spaced. you will see if you take the differences of these samples, you do not create any new samples. You remain within that range, 0 to k minus 1. Okay? So this is the first observation that will help us understand why uniform sampling is bad when you are considering autocorrelation sequences of wide stationary signals. The point is, can we do better? So given k samples, if we take all pairwise differences, we can actually generate, in principle, k times k minus 1 plus 1 samples. Whether they're new samples or not, that's the question. And how many of them can be new in this way, in this fashion, okay? So to understand that, let's assume that these integers m and n are coprime to each other. So we have two samplers which work at two sub-Nyquist rates, which are m factors m and n times slower than this Nyquist rate. So the point is, why do I choose them to be coprime? Because I can use something called the Euclid's identity or the Bezout identity, okay? So if it is a coprime integer, the Bezout identity says that by taking appropriate linear integer combinations of these two numbers, I can span all integers in a certain range, okay? That is the thing that I'm going to exploit in designing my sampler. So the point is, if you have a finite number of samples and if you restrict your sampling instances to these kind of range, so you are actually computing n plus 2m samples, you can create the effect of m times n samples by taking all possible differences between these sampling pairs, okay? That the reason is, whenever you take a difference, in most cases it gives rise to a new sample instead of repeating one of the older samples. So this kind of a design creates many new samples, or in other words, it fills up all the samples which are in between, which you missed because of your sub-Nyquist sampling, okay? So for example, if you take 3 and 7, which are prime numbers by themselves, but they do not need to be primes, they can be all they have to do, all that is near is they have to be coprime. You can create all these integers between 0 and 20, okay? Now, how do we use this sampling scheme for my spectrum sensing task? For spectrum sensing, you remember, you can do it via different methods. You can either compute a correlogram, so you sample your signals at the slower rate, compute the autocorrelation, take its Fourier transform, or you can use filter banks, because filter banks can be implemented by using FFT and makes things faster, right? So what does it mean to have a filter bank which works hand in hand with a coprime sampler, right? So what you do is, you kind of think of as, okay, so if you have an m-channel DFT filter bank, the width of each filter is roughly 2 pi over m, right? So it has that resolution limit. M channels, the resolution is kind of proportional to 1 over m. N channels, the resolution is proportional to 1 over n. I'll show you a way where you can have m plus n channels, but make the resolution proportional to 1 over m times n by combining DFT filter banks in a certain way. So what you do is you create two different filter banks, and these are like oversampled versions of your DFT filter bank. So if you oversample by a factor of m, you create not aliased, but you create images at a spacing of 2 pi over m from basic oversampling properties, right? So you take one filter, you have a filter which has this unwanted lobes, take another filter which has unwanted lobes, but the spacing of between them is kind of coprime to each other, okay? And then you create a filter bank. So you just uniformly shift those filters and have an n-channel filter bank and an m-channel filter bank. The point is, when you consider the correlation between these filter banks, so by the way, each lobe is like 2 pi over m times n. So each lobe is very sharp here, but you have additional lobes. That's what makes the problem ambiguous. But if you consider the cross correlation between all such pairs, you will see that you will create not create, but you will make them overlap and not overlap in certain ways that you will end up with a very fine binning of your DFT spectrum. So this is the way you kind of generate the effect of produce a higher resolution DFT by using only m plus n point DFTs. And if you want to combine them with coprime sampling, so this part of your signal flow graph represents the m-channel DFT. This is the m-channel DFT, and you can further bring down the sampling rate by of course you're using a pair of coprime samplers. So this is how your signal is operating, and you can further bring down the sampling rate by doing standard things like polyphase decomposition. So you can actually make the signal being operated at m times n smaller than the Nyquist rate. So all your operations here are happening, whatever filtering you are doing to implement the DFT filter bank, they're happening at a much smaller rate, okay? So this is how you can create the effect, you can completely leverage the effect of coprime sampling and coprime filter bank in designing your spectrum sensing technique. And just to give you some toy examples, you see that the blue is the Nyquist sample signals and the red is the coprime sampled signal. When I observe it over a finite length of window, you see it is being able to kind of trace this correlation lags pretty well. Of course, if you want higher lags to be estimated, you need to observe for a longer time. But up to this, the two sequences follow pretty well. Okay. Now, a related problem is that of, so far I told you that all you need to do for the spectrum sensing is to just use the fact that it is wide and stationary signal. You do not need sparsity to bring down your sampling rate. So when the spectrum is sparse on top of your being wide and stationary, how can you exploit it? That's another question. So a classical example where a spectrum is sparse is that of cognitive radio, where your goal is to kind of scan the frequency over a wide range and look for available holes. And the holes can be in time and frequency. So the point here is the frequency support of the spectrum changes with time. Your wide and stationary assumption is kind of violated. Okay? So support is not the same. So you cannot say, okay, I'm defining a spectrum. The spectrum changes with time. Okay? So here what you can do is you can use structured sparse techniques in addition to your coprime sampling, for instance, to come up with a good algorithm to take care of this time varying nature of the spectrum. A very simple thing that I proposed, and it works pretty well, that I noticed, was to basically have a time shifted version, compute like short time Fourier transforms, and it can be extended to more sophisticated schemes as well. But let's see how the short time Fourier transform behaves. So if you compute the short time Fourier transform over a certain length and kind of look at its spectrum, of course, because of the inherent assumption that you're looking at spectral holes, the spectrum estimate will be sparse, but it will be heavily corrupted with cross terms, with terms which arise from finite sample averaging, which will give rise to an erroneous term. Okay? So it will give rise to false peaks and things like that when you do spectral detection. So one way to leverage this fact is to do something called a very simple spectral denoising. Okay? So you look at those spectrums, you want to find the sparse. Now you're using the prior information that your spectrum was sparse to begin with, in addition to already downsampling it using coprime sampling. Okay? So this spectrum has already been estimated using coprime sampling, but since it is a short time spectrum, it has this additive noise-like terms to it. So you want to solve a denoising problem like this, and the solution to this is very well known. It's basically a soft thresholding scheme, where your lambda parameter plays a big role. It decides your probability of false alarm or success and things like that. So if you know the statistics of your signal, or if you have a model for your signal, you can choose your lambda to minimize your probability of false alarm and so forth. Okay? So you can design, you can be creative about your design. Now, just to give you an example, if you do soft thresholding versus when you do not do soft thresholding, it really brings down the probability of false alarm rate. And you can see that it kind of, the probability of false alarm, when you increase m and n, you actually need to observe for longer time. So L is the window of observation. So it is kind of very intuitively appealing that you need to observe for longer time when you have higher m sin n's, because you're estimating many more correlation lags. Okay? So with m equal to 29 and n equal to 17, you can actually, in principle, could estimate 29 times 17 correlation lags. So that is why you need a higher observation time, so that the variance in each estimate is small enough. Okay. You can actually extend this idea to 2-dimension, and it can be a talk by itself, but I'll very briefly touch upon this. So the idea of coprime integers can translate to coprime matrices. So there are integer matrices which satisfy something called the Bezier identity. So which means M and N are coprime integer matrices if there exist P and Q coprime matrices, such that MP plus NQ gives you the identity matrix. So if this is the FPD, the fundamental parallelepiped describing the lattice, and if this is the basic unit of the lattice spanned by N, if you take appropriate linear combinations of them, you can actually create this unit lattice, 1, 1, 1, 1. Okay? So if you create that, then you can create all possible integer vectors. That's the point in your 2-dimensional space. So you can have a lattice of M spanned by M. You can have another lattice spanned by N, which are coprime and commuting. They have to commute too. So if they are just coprime, it won't work. So if they're coprime and commuting pair, then by taking this linear combination, you can span the entire integer grid. Okay? And if you restrict them to finite numbers, which is the case for sensor arrays, then also you can have this kind of guarantees over how much you can tile, how much area you can tile. So just to give you an example is that when you do uniform sampling in 2D and kind of try to estimate 2D point sources, using the same number of samples. So coprime sampling and uniform sampling use the same number of samples, but coprime samples can create the effect of more samples by taking this difference in the correlation domain, right? So if you look at the power spectrum plot of the different point sources, this is kind of smeared because it doesn't have enough samples in it. Yes?
So again, is this two-dimensional Fourier transform or is it time frequency domain?
It is two-dimensional Fourier transform, omega 1, omega 2.
Axes of frequency.
Yeah, omega 1 and omega 2, right. Good question, yeah. So, so you can think of them as azimuthal and elevation angle, anything that you can. Yeah. So, so you can see the smearing effect here, but here it is being able to resolve them. That's because it is creating more samples and it is having a longer aperture by creating those samples. Okay?
How do you know you're just not missing things in your coprime?
Pardon?
How do you know you're just not missing things in your coprime sampling?
Here I kind of knew because I had the ground rule, I generated the data. But yeah, in general, there is, you can miss provided if your number of sources and the number of samples have to have a certain relationship between them. They cannot exceed a certain number. That's true. Now that we understood that spectrum sensing can be thought of in a completely different light if you allow structured non-uniform sampling without sparsity, let's see the other picture, okay? Now let's have a sparse model where I will bring in correlation information. Okay? So far I said that sparsity can be used in spectrum sensing to improve the algorithm, improve the detection rate. Now it's the other problem. You have a standard sparse estimation problem, and you're bringing in correlation, correlation awareness to bring down the sampling rate requirements or to increase the level of sparsity that you can recover. Okay? So this is a basic standard measurement model for the sparse. This is basically a standard sparse measurement model where you have measurements in time and space. So Y is like a matrix consisting of measured vectors, where each vector can contain values across like spatial values, spatial samples, and across the columns you have time samples. So each vector is kind of like a time sample coming from a multi-channel data. The multi-channel data can come from many application sensors. You can even think of them as time-varying spectrum if you want, okay? So the standard problem in compressive sensing is they assume that, okay, all these vectors, you can also think of them as a video, okay? Each vector represents an image, a frame. So the standard assumption is that these vectors share a common representation over a dictionary, which is given by A. And this dictionary is an overcomplete dictionary, so it has more columns than the number of rows. And because it is overcomplete, the representation, the representation in terms of the columns of the dictionary turn out to be sparse. Okay? So each individual vector that describes which atoms contribute to the measurement has only a few non-zero elements. And in many applications, the sparse support, like the indices where these vectors are non-zero, do not change that rapidly. So you can assume that over a collection of L such vectors, these vectors share a common sparse support. The goal in these problems is to kind of find this common sparse support, because the sparse support can contain information of interest in many cases, okay? So this model is fairly common in space-time measurement systems, but you can also think of it as a 2D spatial measurement and things like that. So whenever you have two dimensions of measurements and you have sparsity along one of them, you can apply this technique. So this M is the number of spatial measurements, and L is the number of temporal measurements typically. And the goal is to recover the sparse support, the set of indices from M times L measurements. All right. And as I told you, whenever you're capturing an image in time with respect to time, or observing something with respect to time, this model can arise, and these are some areas of application where this model can take place. Now, I will like to point out what the main contribution in this regard is. So the main contribution is the existing guarantee. This is a problem which is very well studied in compressive sensing. Okay, in compressive sensing, the guarantees on the sparse support that tell you, okay, given these measurements, I can uniquely recover S from this observed y and knowing a, they tell you that, okay, you can recover sparse supports as large as order of m, where m is the row size of this matrix. Or depending on this matrix A, if it is random matrix, you can even have a logarithmic of n factor. Okay. Now what I will try to tell you here is that on this model, if you impose some priors in the form of correlation between the signals contained in the non-zero values, you can increase the size of this recoverable sparse support to order of m square. Okay? And this will happen because of two reasons. It will happen because of two reasons interplaying with each other. One is you have some prior that you're imposing on your unknown signal. So your unknown signal is not only having a sparse support which is common over all time, but is also having some correlation structure, which is a fairly common thing to do and which is fairly valid in many applications of interest. So if you have that is what you get. Like the prior comes with the model, but what you design is your sampling matrix. So knowing those priors, can you design your measurement matrix in such a way that it will exploit that prior and increase the level of the recoverable sparse support? So what is the prior that I'm going to use? I'm going to use the following prior, that between two signals which occupy two different non-zero indices, the correlation is 0. So you can think of these source signals kind of trying to coming from independent sources or uncorrelated sources under a milder assumption. If they're independent, that's great. Then you have even more priors to exploit. But let's say they're uncorrelated, these time samples, which is the case when you have multiple source estimation, source localization problems. It's often the case. So if you have that kind of a situation, then can you design a better A so that you can estimate way larger support using fewer measurements? Okay. And this sampling often exploits the physics of the problem. So sometimes you just cannot choose any A that you want. It comes associated. It comes with a certain structure which exploits the physics of the problem. So if you really so let's see how we can think of designing this matrix, say. Okay. So let's say you compute the correlation of this data, the correlation matrix. And this correlation matrix can be equivalently represented just instead of looking at a matrix, if you look at a stacked up vectorized version of that matrix, which is an equivalent representation, you will see that this representation is basically this vector lies in the range space of this matrix, which is called the Khatri-Rao product of this matrix with itself, A with itself. It's kind of like a column. It's not kind of. It's exactly the column-wise Kronecker product of the matrix with itself. Okay, so it's a sub-matrix of the Kronecker product of A with itself. Now the point is, what do we gain by looking at the correlation matrix in this kind of form and trying to understand what role this matrix plays? Another thing that you might want to notice is, because of our assumption that this correlation, there is no correlation between two non-zero elements, this vector P that you get in the representation of the correlation matrix also turns out to be sparse, and not only that, it has the same sparse support as any of these vectors. So if your goal is to recover the sparse support, instead of recovering it from the raw data itself, you can think of recovering it from this matrix Z. Why is it more useful? Because this matrix Z automatically incorporates the information that the cross terms in the correlation matrix are 0. Okay? So somehow this model makes use of that constraint, of that assumption. Yes, Petash, you had a question.
What's P again?
Which one? The P? Oh, the P is basically the vectorized version of this matrix, Rx6, the inner matrix. Yeah. So the original problem is find sparsest X satisfying these equations. You somehow, looking at the correlation domain, your problem equivalently becomes find sparsest P satisfying this kind of an equation, right? Now what do we gain? Going from A to all we gained is basically this measurement matrix. Now instead of looking at A, you're looking at this Khatri-Rao product of the measurement matrix. And if your A has to satisfy certain properties, right, for this sparse reconstruction to be successful. Now the point is, with respect to those same properties, is AKR a better matrix in some sense than A? If it is, then you gain something by solving this problem instead of solving that problem. If it is not, you gain nothing. Okay? So that's what we are trying to understand, whether this AKR is fundamentally a better matrix than A for sparse recovery. to understand what we mean by better, we can talk of this at several levels. At a very fundamental level, or maybe I should say, for the sparse reconstruction technique to be useful, to be uniquely producing the sparse solution that we are seeking, the fundamental condition that needs to be satisfied is the Kruskal rank of this matrix, right? So this is a very well-known theorem in sparse recovery, that if your sparsity, if your size of the sparse support is less than the Kruskal rank of A, then you can recover A. Then there is a unique decomposition, unique sparse decomposition. Whether or not you can recover it, that's a different question, because recovery might be combinatorially hard unless you do some convex relaxation. Okay. Now the point is, just by looking, so basically this Kruskal rank kind of upper bounds the size of the sparse support that you can recover. Now by looking at A versus AKR, can we say that the Kruskal rank of this guy is really, really larger compared to that? Now unfortunately, there is no easy way to relate the Kruskal ranks of these two matrices. Okay? It really depends on the design. You can only have some very loose bounds relating the two Kruskal ranks. So Kruskal rank of AKR in general will be always strictly larger than that of A, but the larger can be, it can be twice as large. It need not be m times as large, okay? And of course, it is of course less than m squared, because Kruskal rank is less than rank. Now, so basically you see that there is a whole range in which the Kruskal rank of this new matrix can lie. And where it lies decides how much sparsity you can recover. So the point is, can we use structured sampling to increase the Kruskal rank of the matrix? That's the question. To motivate this question, I'll give you an example of source localization in antenna arrays, because that way I can introduce one of the sampling geometries that I kind of proposed during my PhD. So source localization antenna arrays, basically you have a bunch of antennas and you have a bunch of sources which are coming from different directions. And this assumption is very much valid, that sources from different directions are statistically uncorrelated. Okay? And your sampling matrix is basically determines the position of these antennas. So if designing A means basically designing these antennas, how you space them. Now if you want to recover sparse support which can be as large as order of m square from this kind of a model, then you are actually talking about the number of sources. That is exactly the correspondence between the sparse support and this problem. So we are directly interested in a question where we can localize these sources where d is order of m square, and it is a very non-traditional scenario because all classical source localization algorithms work in the domain where d is order of m. They do not go beyond that because there is some practical difficulty that you will see, because the covariance matrix can only have rank up to m, and if it has rank more than m, then you cannot do subspace decompositions and get information. Okay? So once again, to motivate this approach is, similar to uniform sampling, sensor arrays typically arrange their antennas in a uniform fashion. It's called the uniform linear array. The uniform linear array difference set, the same, you remember the pairwise difference I was talking about? The same pairwise difference also arises in this correlation model. But it's now the difference between the antenna positions. So you will see that it doesn't create any new antenna positions, right? And this is primarily the reason why you can only recover order of m sparsity. Now, the point is, if the sampling scheme is kind of the spoil sport in this case, can we be smarter about placing our antennas? So a very simple way to show that this is indeed possible is by the so-called nested array design. Okay? So what you do is you take the same number of antennas, m, you divide them into two halves. Okay? So you place one half uniformly, you place the other half also uniformly. So it's a very modular kind of design. You are taking two ULAs which are kind of subsampled version of each other, and the rate at the spacing of this ULA is directly related to the number of elements in the first array, because my goal will be to somehow create the effect of this dense array in between this sparse array, to recreate all the samples that I missed by placing my antennas in this fashion. And you can indeed do it. If you consider the differences again, you will see it exactly spans the entire stretch of your entire the aperture of your antenna without missing a single element. Okay? Now if you look at the Kruskal rank point of view, okay, what does it mean for the Kruskal rank of these matrices? So for source localization examples, under narrowband assumption, your matrix A has this kind of a specific form which is like a Vandermonde dish matrix. It need not be van der Waals because V1, V2 in general are not consecutive integers, okay? But let's say it's sub-matrix of some van der Waals matrix. If you look at the Kruskal, if you look at the Katrira product, you will see that the van der Waals matrices create all these differences in the indices, okay? And that way, you can actually make them span a van der Waals matrix with consecutive rows, with order of m square consecutive rows. And that itself guarantees that the matrix is full rank. Yes?
So, in the nested case, you're also working the far field regime.
In the far field regime, yeah, this is not valid anymore because in the far field regime, you have to consider the curvature. You cannot assume plane waves anymore. Sorry, near field regime, you mean? Near field regime, right. Yeah, yeah. Far field you can. Far field is plane wave, right.
Right, because in a sense, if you have 100 antennas, you put the first 50 here, and then the rest of the 50 you need to space them.
That's right. So what? Right. So what narrowband and what near field means depends on the aperture of the antenna. That's very true, and also the wavelength. That's very correct. Yeah. So it's not the conventional. Yes.
So essentially, so what pops up into my mind that you have two fundamental frequencies for this array.
Yes, that's right. Sampling frequencies for this array, right? Uh-huh.
But apparently you have some, because of what you're doing here, it's not just limited to fundamental frequencies, it's sort of like the product of those.
Exactly, you can think of it like that. Yeah, correct. The spacing decides somehow. So the final position where I put the last antenna is kind of the product of the first number and the spacing itself, right?
So you have lots and
lots of frequencies.
Spectrum frequencies.
Yes. Now, again, typically you do not obtain perfect correlations. You always have noise and errors coming from finite snapshot averaging. And one way to kind of take that into account is to explicitly model those finite snapshot averaging effect in your model, okay? So nothing is perfect. So basically your RXS is only approximately sparse. It is corrupted by this additive noise. But this additive noise is an interesting property. It is a function of L, so it changes with your number of samples that you average, and it goes to 0 as L tends to infinity. Okay. So if you have that kind of a model, and then let's say you have more assumptions on your signal model, you assume Gaussian sources and so forth, then what you want to do really is just want to solve once again, not a denoising problem, but a lasso in this case, because there is a matrix, fat matrix A. If there was no matrix A, then it would be a denoising problem. So you want to solve a lasso like this. First term takes care of the noise, second term takes care of sparsity, and you also have positivity constraint because you're looking at powers in the correlation domain, okay? So using this, can you lower bound the probability of support recovery? So yeah, if you have certain assumptions, if your sparsity is kind of inversely proportional to the coherence squared, typically the sparsity has to be proportional to 1 over coherence. But since you're looking in the correlation domain, you can show that the Katrira product matrix, the coherence strictly becomes square of the original coherence, which means the coherence goes down. So you build a better dictionary actually by going to the Katrira product domain, okay? And if your regularization parameter belongs to this kind of a range, which is related to the sparsity and coherence, and also the lowest signal power in your data, then you can show that okay, you have probability of support recovery kind of grows to 1 exponentially fast with the number of observations. Okay. So I'll show you quickly 2 numerical examples. This is a regime where sparsity is more than your number of measurements, which is typically not considered in the computer sensing literature. And you can see I compared 3 algorithms. This one does not use correlation awareness, and these 2 kind of uses correlation awareness because of the models that they use. And you see when the number of measurement vectors is small, these algorithms are not that great because of that additive noise factor, okay? But as the number of measurements grow larger and larger, the additive noise becomes smaller, and so the probability of success increases for both the algorithms. In a regime, yes?
What is your RPN you mentioned here? So
M is 20. N, I think, was 256, if I remember correctly, yeah. And I'm wearing L. So but if you consider the other regime where sparsity is less than M, then all these algorithms will work because typically all these algorithms are designed to work for sparsity less than M. And you can kind of get a comparative plot. Again, now you see the lasso and co-SMB somehow is sloppier because of the same reason. Because the other algorithms do not have this additional artificial noise-like term coming from cross correlation. For a noiseless measurement model, they are actually operating on a noiseless like measurements are truly noiseless. But this lasso kind of going to the correlation domain is introducing additional cross terms, which kind of spoils the algorithm for low snapshots. So there is much work that can be done in this regime, I believe, to strengthen the algorithm. Okay. And of course, you can extend this nested array to higher order statistics. We have some work on that. So when you not just exploit the correlation, but let's say the kurtosis of your signal, which is the case for speech, for instance. So can you extend this sampling scheme to that kind of a scenario? So I'm not going through the details, but yes, you can. You look at something called higher order difference sets. You can do it in one dimension. You can do it in multiple dimensions. It becomes a little bit more messier. And your nested scheme can be extended by extending to more than 2 levels. If you understand the principle under which this nested sampling occurs, that your spacing is related to the number of elements in the previous level, that way you can increase your spacing that way and create a 2qth order difference set instead of a second order difference set and recreate those samples again. Okay. Now, finally, I want to talk about some work that I recently did with my graduate student Hung. He's here. It is basically talks about sketching covariance matrices. So matrix sketching is something which is becoming more and more popular these days because you sometimes compute outer product of your data, and you kind of try to capture the information from those outer products. They give you a compact representation of your data, and they also lead to natural ways to reduce your dimension. So how to form compressive sketches of covariance matrices when you have like streaming data applications. So imagine you have n channels, again, something like the MMV model, but you're looking at now your goal is to compress the covariance matrix of this data. So you have this streaming data example where your covariance matrix, let's say, has a size n by n, right? Because you have n channels. And your goal is to first compress these n channels into m subchannels, where m is strictly less than n. So you're reducing this dimension. You're also reducing the time dimension by computing the outer product. So this dimension somehow vanishes, and you get an m by m matrix, which is a much smaller sketched version of your original covariance matrix. Okay, so if your original covariance was n times n, this is an m times n matrix. The first difference that you should notice about this kind of sampling is the sampling is no more linear. Okay, so if you reduce a vector to another smaller vector, you typically do it by y equals ax. This is compressive sampling, something that lies in the heart of compressive sampling. When you do that kind of a quadratic sampling, when you do that kind of a sampling of your covariance matrix, the sampler becomes a quadratic sampler, because you see each element here depends, it's kind of a quadratic product of the elements of your matrix, aij times amn, right? Each element is a linear combination of that kind. So how to exploit a quadratic sampler when it's no more linear, okay? But your sample that you're designing is linear. So you're designing a linear sampler, but you're trying to impose good conditions on the quadratic sample that comes as an effect, as a byproduct of this operation. This is a very interesting question, actually, and it can be extended to more nonlinear structures, I believe. So, so as I told you, this is kind of like a sketch of this covariance matrix. For many reasons, you do not want to store the entire covariance matrix. You want to store a sketch of it. But the way you sketch the matrix, you get a quadratically sampled version of your covariance matrix. And by looking at different structures of RxX, you can actually design a good sampler versus bad sampler, so that you can recover the original data from your sketched version. So one thing that I proposed was, it has nothing to do with the nested array. I mean, it has something to do with the nested array, but it is no more an antenna design problem anymore. It is like sampling a matrix, but it draws inspiration from nested sampling, from the way I placed antennas in the nested sampling. So you design a sampling matrix where you place your ones and zeros in a certain fashion, okay? What is that fashion is defined in this way. Let's say this is some function that you get by maximizing this, an integer valued function. So you place your ones and zeros in a certain fashion, so that for certain structured matrices, this can give you good sketches and lead to a lot of compression, okay? So the class of structured matrix that I'm going to consider is, let's say, we look at a Toeplitz matrix, because Toeplitz matrices describe the covariance matrix of White's and stationary vector Gaussian processes, right? So if you have a Toeplitz matrix, remember, I do not have access to this matrix. I cannot just take this matrix and compress it. If I could do that, I'll just take its first row. That's it. Your symmetric Toeplitz matrix. Right? There is nothing to compress. I only have access to data that I'm compressing, and as a byproduct of that, when I'm taking the inner product of those compressed samples, I'm getting this sketch. So I do not have access to this matrix. I have access to only data that has this kind of a covariance matrix. So this generalized sampling actually designs A such that those quadratic samplers can pick and choose these elements from the Toeplitz matrix in an appropriate fashion, and gives rise to a non-Toeplitz sketch which kind of takes these distinct values and scrambles it up inside the smaller matrix. Okay? And that way you can gain order of n, square root of n compression just by exploiting the structure. No need even to exploit sparsity so far. Okay? Now, what happens if the Toeplitz matrix is also sparse? That's the next question, right? And of course, your data will not necessarily be sparse in that case, right? Your Toeplitz matrix can be sparse, but you cannot see the sparsity in your data right away. But can you still design your A in a clever fashion? So we showed that you can do that by concatenating a structured matrix with a random matrix. Okay? So the approach that we have so far, you consider two sets of samplers. One is, this is a structured matrix, structured sampler, and this is a random sampler. So again, a random sampler, which is independent of this random sampler here, and again a structured sampler here. Okay? And this one has P1 rows, so you're ultimately reducing your n-dimensional data to P1 dimension, and here you have P2. So you have total P1 plus P2 measurements. Okay? And then you're computing autocorrelation of these individual matrices and also taking cross between them. If you do that, then it is possible to show that under this kind of a sampling operation, if your sparsity satisfies this relation, this k and psi are functions of the generalized Nyquist sampler, which I defined earlier, okay? And if your number of rows satisfies is large enough, it's at least as large as the sparsity, or k times k of n. So this function, if you look at it carefully, it will be order of n to the power 1/4. So your measurements only need to be at least as large as the sparsity, or if the sparsity is much smaller than order of n to the power 1/4, then it needs to be at least order of n to the power 1/4. Then you can have a unique decomposition with high probability of your compressed matrices in terms of the true matrix. Okay? So this is the take-home point. And now when you have uniqueness, how do you recover? Uniqueness is fine, but recovery itself might be a completely different ballgame. So you typically try to recover by a L1 minimization, but you have a Kronecker product structure instead of a simple linear B1 times V kind of relation. Okay? So you have to take care of this Kronecker structure because it's a Kronecker of two random matrices. So you have to look at the RIP coherence of these kind of structures. And you can also show that, okay, if your sparsity and is small enough and the P1 and P2 are large enough, which are slightly stricter conditions compared to the uniqueness condition, because uniqueness has to be there. But those same conditions need not guarantee the recovery of the sparse problem. Okay? So these are stricter conditions compared to the uniqueness condition. And then you can recover the original matrix by solving this problem, which I call P1, with probability at least 1 minus 2 epsilon, where epsilon is related to your measurements in this fashion. Okay? So these are some of the interesting initial results that we got in this regard, and we are further exploring more structures in terms of low rank and so forth. So those were the three distinct flavors under which I wanted to unify the idea that correlation, sparsity, additional prior information can work hand in hand and reduce your sampling rates much further beyond what is known, okay, what is traditionally possible to be known. And some of my ongoing and future directions are basically, you saw that nested array says that, okay, you can do order of m square and so forth. But what is the converse for that? Okay, so if you have a certain statistical model, what is the fundamental sampling limit that you have to kind of satisfy? Something akin to the red distortion theory, let's say. So that is one of the questions that I'm trying to answer here. And in many cases, you know, in these cases we assume we know the dictionary, we know the representation. In many cases you do not know that, okay? So you have to learn the dictionary as well as the representation from your data. So in that case, does this correlation priors really help you in learning the dictionary, or does it hurt? So those kind of questions I'm very interested in exploring, and also learning of hyperparameters from your data. Does this correlation information help you learn it what should be the learning algorithm that should exploit such information and so forth. And another interesting idea is all these dictionaries that you notice so far, they consist of discrete atoms, right? So the point is, most dictionaries in comprehensive sensing are discrete dictionaries, finite dictionaries. But in reality, when you consider parameter estimation problems, your parameter can span a continuous range, okay? And the dictionary that gives that, you cannot even talk about a finite dictionary anymore. It can be, you know, a linear combination of those atoms, and there can be an infinite number of such atoms. So for those continuous dictionaries, what is the right way to go about these problems? So there has been some good work on recently on atomic norm minimization, which can find very good connection to this kind of problem, which is also one of my research interests. So here are some references which I kind of want to cite for this talk, and thank you very much for the attention. So I can take questions. No questions. Yes, yes, Neil.
In the beginning of your talk, you showed a comparison between the Nyquist sample and the coprime sample, right? You had this.
Right. Somewhere.
Shouldn't those go to the same in some kind of limit? Shouldn't they equal each other? Because they were sort of different.
No, because the rates are different.
Okay.
Nyquist sampling is happening at a much faster rate.
Okay. So
Yeah.
if you were to then sample your coprime rate at the same rate, should they get exactly?
No, you always sample coprime samples are always operating at a slower rate.
Okay.
And you choose the slower rate. And because of the slower rate, you have to observe for longer. So that is the price you pay. So you save on power.
Okay,
but
but
yeah.
you never, but just to test your coprime method or something, you wouldn't sample the night. You wouldn't go up to the Nyquist rate just to make sure that the two things.
No, you don't have to. That is the point. You don't have to go to the Nyquist rate. You could, if you could go to the Nyquist rate, then there are advantages of that. But the point is, you can get similar performance by doing sub-Nyquist sampling,
Right.
provided your reconstruction or estimation algorithms are good. Also, they work hand in hand with the coprime scheme. So coprime sampling has potential, but to fully utilize the potential, you also need a good estimation algorithm. Yeah. Yes.
So do you actually have to sample for much longer to recover your
Yes.
spectrum?
So-
and do you win anything at all?
Yeah. So that's a good question. So it depends on which domain you are looking at. So if you're sampling in time, then you have to observe over longer windows. That's for sure.
But how much longer?
Yeah.
That's the question, right? So how much longer depends on the signal model. So it depends on actually how you model this error term here. Okay. This error is decaying fast enough or not, okay? So depending on the distribution of your signals, how this error is behaving, that decides. And having a lasso-like algorithm helps even if you have noise, because compressive sensing algorithms have very good robustness properties. So even if there is noise, they can kind of pick out the sparse solution. So that is why if you do a simple spectrum estimation alongside coprime sampling, that can have poorer performance compared to if you combine lasso with your coprime sampling and exploit the sparsity as well. So it is a function of the algorithm you're using. It's a function of the statistical model that you have on your signal, I would say.
Fundamental assumption is wide sense.
For the first part it was, yeah. But in general it need not be. So if you violate the Whiteson solution assumption, you can always incorporate them as an additive noise, provided you model that noise appropriately. Right. Yeah.
With Nyquist rate sampling, it's fairly easy to show that the reconstruction is lossless and such. With coprime sampling, do you also have some?
No, you do not have lossless reconstruction of the signal, but you have lossless reconstruction of the spectrum. So you cannot.
Which is more or less.
No, for random processes they are not, right? So you cannot get back your random waveforms anymore, but you can reconstruct the power spectrum losslessly. That's the point. So that is the fundamental guiding factor that you are losing. That's a very good question actually. You are letting go of something. There is no free lunch. What you're letting go is the ability to recover the waveform, the signal itself for all the time. But what you're getting is a very accurate representation of its spectrum. That is how it is happening. Yeah. So it is lossless with respect to the spectrum, not with respect.
This can be shown, huh?
This can be shown. Yeah.
And if your stationarity is violated?
Yeah, that is why stationary violation, I think, is a very interesting topic. You can either think of it as, clubbing. One simple way to model it is to club it as an error term and kind of say that, okay, it has a certain time distribution which varies with time. Or you can have a dynamic approach where you kind of adapt your spectrum sensing at each stage, something like a Kalman approach, okay? So you can have a non-stationary model for your signal and say that, okay, my Whiteson stationary assumption is no more valid, but let's say I'm still using my coprime sampling. I want to see how it performs. So under appropriate non-stationary assumptions, then you go about analyzing the algorithm iteratively at each stage. Yeah.
How about if your signal is not just Whiteson stationary, but actually stationary?
If it is stationary, then actually you have the same PDF, right? Then you have more. Then you can exploit probably more properties of the signal. Then you can kind of say that, okay, it has the same distribution across time, right? So yeah, I think there is more that can be exploited.
In practice, Whiteson stationary is used as assumption because it's simpler and you can do a lot of things with it.
Right.
But in fact, in reality,
that's right. In reality, most things.
I don't see a reason why it would be Whiteson stationary and not stationary.
That's true.
Sometime in the
That's true.
It should be stationary.
That's true. Exactly. That's very true. Yeah. So if you use stationary assumption, then you can do a lot more than just using Whiteson stationary assumption. Then you can use higher order moments also probably. Okay, which you do not assume that they also then can have this special structure. So not only the second order moment is a different structure, then you can probably have higher order moments which you can also use of the distribution. Yeah. Question.
I had a claim that the Bezu identity was in fact obtained by somebody in India a long time before Bezu.
Really? Oh wow, that's interesting.
Vidyasagar.
Oh, okay. Vidyasagar said that, yeah. I see. Interesting. Very nice. Yeah. Okay. Questions? More questions? No?